Hello. In today's video we're going to be looking at our first lecture within Chapter 19, looking specifically at Learning Objectives 2 and 3, where we're looking at our second and third law of thermodynamics, defining entropy, and looking at that entropy change for a phase change. Okay, so to understand entropy, and our thermodynamics, we need to look at enthalpy first, then we'll go into entropy and spontaneity. Okay, so talking about enthalpy change, we're talking about delta H. So keep in mind, enthalpy itself just tells us kind of the direction of heat. So enthalpy change tells us if a process is exothermic or endothermic. So is it absorbing or releasing heat? Okay. Now, this does not tell us if a process will be favored. So, by being favored, this is going to be something that is spontaneous. So it doesn't tell us if a process is spontaneous or not. There are plenty of processes that are exothermic that are not spontaneous, or endothermic and spontaneous. So, example of exothermic process that is not spontaneous would be the combustion of methane. Okay, so combustion of methane would be an example where we do not have a spontaneous process. And then we could also look at endothermic processes that are spontaneous. For instance, melting ice at room temperature. This is a reaction or a process that will cause us to be in a more disordered state, but it requires energy. So this is a spontaneous process that occurs naturally, but it requires energy, so it's endothermic in nature. So enthalpy is not the only thing that tells us about whether a process is favored or not. We also have to look at what's called entropy. That must also be taken into account when determining if a process is favored or not. Okay, so another thing to keep in mind is that we were talking about thermodynamics, which tells us the direction or extent of a reaction, not kinetics, the rate of a reaction. So a spontaneous process itself, thermodynamically, is possible, which means that we can have this reaction occur. But it can still be very, very slow. So we're talking about a spontaneous process, we're talking about the thermodynamics of it. There are lots of very, very slow reactions that are thermodynamically favored, which we talked about during the kinetics chapter. Okay. So, if we have a spontaneous process, we have a process that is irreversible. And that's because a spontaneous process in one direction is non-spontaneous in the other direction. Okay? And if we have a spontaneous process, our delta S of our universe will be greater than 0. Keep in mind that our delta S of our universe is equal to our system plus surroundings. So one of them is going to increase in such a way that our delta S of universe would be 0. Doesn't matter if it's the system or the surroundings. So our entropy, since we deal with most of the time spontaneous processes, right? Or if we're dealing with a non-spontaneous process, it has to be coupled with a spontaneous process. Because of that, our delta S of our universe will always be increasing, so the entropy of the universe is always increasing. Okay, so we can increase our entropy in a couple different ways. Not just these ways, but these are the ones we're going to be able to recognize ourselves through a couple of different phase changes, such as solid to liquid, solid to gas, or liquid to gas. So going from a higher order state to a higher disorder state. We can increase the number of moles in the gas phase. And we can also mix components of molecules. So we can take two elemental form things, combine them to produce a compound. So a reaction, basically a reaction that goes from elements to a compound, such as N2 plus O2 going to 2NO. Where we have all the same number of gas molecules, but now we're mixing elemental form things with, combined to make a compound. Okay, so let's predict some of the signs down here. So if we have N2O4 going to 2NO2, we start with one gas molecule, we go to two gas molecules. So we're increasing the number of moles in the gas phase, so our delta S here is going to be greater than 0. I2 gas going to I2 solid. If we are at the correct, here we're going from a gas to a solid, so we're going in the opposite direction of what entropy says we should. So this will be a delta S that is negative. Okay. And then melting of ice at negative 20 degrees Celsius. Doesn't really matter what temperature we're at. Melting of ice, going from ice to liquid, will always have a delta S that is positive, right? Now, this, again, our delta S by itself of our system doesn't actually tell us if we have a spontaneous process or not. So this one right here, for instance, would not be spontaneous. And this one will only be spontaneous at certain temperatures. So just keep that in mind. And one other thing I wanted to talk about, bring into this idea is the idea of a reversible process. So if we have a reversible process, we take those processes are ones that are carried out in a series of infinitesimal steps. And that's the only way that it can be considered reversible. right? So they're infinitesimal, so neither the system nor the surroundings are actually experiencing energetic changes, so that they can go back to the system and surroundings the same way they were before the change. So we basically say that our system and surroundings don't change. During that reversible process, so our delta S of our universe in this case for a reversible process will be 0. Okay, so our reversible processes is non-spontaneous. Typically, they're also not non-spontaneous. They're just neither. So we don't really look at the spontaneity. There's not a direction in a reversible process that is spontaneous and the other one non-spontaneous. Neither process is considered more spontaneous than the other, I guess. Okay, so let's look at our entropy within changes within a system. So if we're talking about entropy, we're talking about delta S is equal to S final minus S initial. So a little bit different than what we see with delta H. So delta H is delta H final minus delta H initial. So we look, these values have no delta associated with them. And when we're talking about changes of entropy within a system, we're talking about changes in randomness. More randomness, more entropy. Less randomness, less entropy. And that can be fairly clearly seen when we're going from solid to liquid to gas. We can see that as we add that energy in, we add a lot of movement, and that movement can lead to randomness and disorder. We can also see that when we go from fewer gas molecules to more gas molecules, so going from N2O4 to 2NO2, we see that going in this direction, we increase our number of gas particles. And then going in this direction, we decrease that. And doing the increase in the gas particles, we have more disorder. And then going in the opposite direction, when we have fewer gas molecules, we have less disorder. Okay. So the changes for entropy, if we have, so we're talking about delta S of our system. So if we have a delta S of our system for any process involving the reversible transfer of heat, we have the following equation. Our delta S is equal to our Q rev over temperature. So we have to have an isothermal process. So here we have a reversible heat transfer going on. An example of a reversible heat transfer would be freezing, or a phase change in general. So we can look at, if we have, this is a reversible process, our Q rev will equal our delta H. So we can figure out a phase change. So we can figure out our delta S of our phase change by taking the temperature beneath our or enthalpy of our phase change. So it could be delta S of fusion, for instance, equal to our delta H of fusion divided by temperature. Okay, and it's because, so this is true if we have a reversible process. So I already kind of hinted to this, but entropy itself is affected by molecular motion. The more motion, the more randomness you introduce into the system. So more motion, more randomness. Right, so we're increasing our temperature, our random motion is increasing, which increases our entropy. So, increased temperature generally leads to increased entropy, as long as we're staying within the same state. Okay, let's see how you guys are doing with this material. So, let's look at the following statements and determine if they are true or false. So the first question says entropy change, or the first statement says entropy change is a state function, and this is true. So it's a state function, and we're going to be able to utilize that idea as some things we can only calculate, some entropy changes we can only calculate assuming a reversible process. And then, since the final initial states don't matter, we can use the information we got from the reversible process and apply it to an irreversible process. Okay, if a system undergoes a reversible change, the entropy of the universe increases. That is false. Hopefully you guys remember delta S of our universe is equal to 0 if we have a reversible process. Does not mean that our delta S of our system and its surroundings remains 0, but our universe remains 0. Okay, if a system undergoes a reversible process, the change in entropy of the system is exactly matched by the equal and opposite change of the entropy in the surroundings. That is true. And that's, again, where we get this idea. And then if a system undergoes a reversible process, the entropy change of the system must be 0. That is false. We do not have to have a 0 entropy. We just have to be able to reverse back and get back to the same state that we initially got when we have a reversible process. Which is why we have to have a 0, right? If we have an increase in our entropy of our universe, we can't get to the exact same state we're at when we go in the opposite direction. So we have to have a delta S of our universe being 0, but if we have them equal to each other, then when they go back in the opposite direction, they'll be exactly like they were at the beginning of the process. Okay, let's try one more. So we've got gallium freezing at 29.8 degrees Celsius and has a delta H of fusion of 5.59 kilojoules per mole. We want to know what our delta S is in joules per Kelvin when 60 grams of liquid gallium solidifies at 29.8 degrees Celsius. Okay, so in this case we're looking at our delta S of fusion. It's going to be equal to our delta H of fusion divided by our temperature. Okay, so first we want to figure out what our temperature is. So our temperature of fusion, we need that temperature be in Kelvin, so we're going to take 29.8 degrees Celsius, add 273.2, giving us 303.0 Kelvin. Next we want to figure out our H of fusion, enthalpy of fusion in joules, right? So we need joules per Kelvin, so we're going to take our delta H of fusion, go from kilojoules per mole to joules per mole. And now we need to take that joules per mole and convert it into just joules. So we need to multiply that by our moles. So we're going to take our 60.0 grams of gallium and convert it into moles of gallium. Using our molar mass. And then we can take that, multiply that by our negative 5590 joules per mole, giving us negative 4,810 joules. Now we're going to take that value, put it in with our temperature to get our enthalpy. This gives us a value of negative 15.9 joules per Kelvin. Okay, that's everything in this video. See you guys later.